Hello and welcome, friends, to another Python tutorial for MS365. And if you aren't in class with me and you just happen to fumble across this channel looking for some help with business analytics, working with Python, working with SKlearn, stick around. Hopefully I can help you out a little bit. So let's just jump right in because this is going to take a little bit of time. And I want to talk to you a little bit about the way you would do multiple regression when you're working with statistics versus the way you would do it if you're trying to create a predictive model. So when you work with statistics, you take 100% of your data, and 100% of that data is used to build a model that explains the relationship between the independent and dependent variables. And we do like that, but when you're working in predictive analytics, specifically for models that you want to actually deploy, you do something called data partitioning, and that's what we're going to do today. So in order to get started, I'm going to talk to you about data partitioning. Let's just go ahead and jump in and do a little bit of Python, import some libraries, do some work. And along the way, I'll explain how all that works. So our goal today is to do a regression with partition data using SKlearn. So what we're going to do first is, if you're working with me, I've given you a data set on Canvas called marketing data. So we're first going to import some libraries. So we're going to need pandas. We're going to need matplotlib. We're going to need SKlearn, but we only need some of SKlearn. So instead of importing it all, we'll do SKlearn linear model. Import linear regression. Okay, so we're going to import from SKlearn the linear regression model. So there are two new things that we want to import to go along with it. So we want to partition our data, and I'll talk a little bit more about how that works. So we're going to import from SKlearn model selection. And you'll have to forgive me, I'm using a different keyboard from what I normally use, so my typing's a little off today, but we'll make it work. Okay, so we're going to import from the SKlearn library test train split or train test split, and we'll look at how that works. What that's going to do is partition our data for us. Then once we build our model, we're going to want to evaluate it. So in order to do that, we're going to need some metrics, right? We're going to want to do our root mean square error, and we're going to want to do our mean absolute error. So in order to do all that stuff, because we don't want to do the nasty math to make that work, we're going to go from sklearn.metrics, and we're going to import a few things. We're going to import mean absolute error, and we're also going to import mean squared error, like so. So with that, we have now imported all the libraries we're going to use for this. So I assume that you guys did come to class, so you know what the SKlearn library is. If you didn't come to class and you don't know what SKlearn library is, it's one of the more popular machine learning libraries for Python. You should definitely check it out. It's in the book. I've got a couple other videos on it as well, and we talked about it in class. But in the interest of saving time, I'm not going to go into it very much. Just know that we need these three little segments of it. We need the linear regression model, we need the train test split function, and we need these two metrics, mean absolute error and mean squared error. So first thing we do, let's do some exploratory analysis. Let's just take a look at the data that I've given you. So I've given you this marketing data, and if you're following along not with class with me, it's pretty common data that's out there. If you go to Kaggle, you should be able to find it, no problem. So first thing we're going to do is we're going to just read that into our data frame. So we're going to read CSV, and we're going to grab our marketing data and pop that in. Oop. Marketing data. There we go. And paste that in like so. All right, so let's talk about what we've got. So in a nutshell, we have three different areas of marketing that we're spending money in. So think of this like money in the thousands. So we're spending a set amount of money to advertise in three different mediums, and we're then looking at our target variable of sales coming back, right? So we've advertised in YouTube, we've advertised on Facebook, we've advertised on the newspaper, and then we've got our corresponding sales that are coming from that, okay? So what we're interested in looking at is how much predicting power, how much influence on sales advertising in YouTube, Facebook, or a newspaper might have. Maybe all three of these predictors have a great impact or influence on sales. Maybe only some of those have a great impact on sales. So what we're going to do is this brute force approach where we're going to take all three possible predictors. We're going to create a multiple regression, and we're just going to see what happens. And then if we want, we could go back and remove one of the predictors and see how that change impacts our final regression scores. Okay, so what we're going to want to do first is create some variables for our predictors. So again, I assume that you've read through the book on multiple regression, so you understand about the linear regression function or formula, y equals mx plus b. You understand multiple regression, and you're here more for the coding side of things versus the lecture side of things, which I've got a lecture on that too. Okay, so what we're going to do, since we've decided that YouTube, Facebook, and newspaper are all going to be predictors, is we're going to set up some variables first. We'll just set up a variable called predictors. Okay. And what we're going to do is we're going to just list inside this variable. So we're going to create a list called predictors, and we're going to list off whatever predictors we want to be in our multiple regression. So we're going to take YouTube. Move that out of the way. We're going to take Facebook. And we're going to take newspaper. Okay, so now ultimately what this is going to be is this is going to be our X value when we work with SKlearn, when we actually train our model. These three different predictors will be it. So what I'm going to do is I'm going to create another variable called X. Okay, and I'm going to say that X is a data frame, our original data frame, with our predictors as variables, or excuse me, as columns. Okay, so now if I do this, just to show you what that'll do, assuming I spelled everything right, is check this out. So if I do X, it's going to automatically give me YouTube, Facebook, and newspaper. So it's basically that original data frame without the target variable of sales. Okay, and when I say target variable, remember we're doing multiple regression. So with multiple regression, or just linear regression in general, you're going to have a continuous value, single target output. So it's going to be a number that can be a continuous number, any number you want, but it's going to be a single output value. So you're not getting a multiple output, and it's got to be a continuous value, numerical value. Okay. So now we're not quite done. We still need to do something. We need to tell it what our Y value is going to be. So now the Y is pretty easy. We've decided that the Y is going to be our sales, right? Remember, Y has to be a continuous single value. So we're going to say df sales, and it's lowercase sales. Okay. So now when we do that, if we just look at Y, we've got our outputs, or we've got our target values. And if we look at X, we've got our predictor values. So things are looking pretty good so far. So now this is where things start to diverge a little bit. If we were working in traditional exploratory, explanatory statistics, at this point, I would just fit a model. I would take all of this data, all 171 lines of data, and I would fit it to a linear regression. I'd just be done, right? So I would do model fit, I'd be done. I could look at my R-square, call it a day. But we don't want to do that, because remember, when we work with predictive analytics, we want our model to be able to generalize. Okay, so what does that mean when we say generalize? So we want our model to work well with data that it has not seen. We want to actually use it in a production environment. We want it to be deployable versus simply being able to work with the data that it knows already. So if I give it 100% of the data, what it's going to do really well is it's going to fit a model that really, really understands this 171 lines of data. But what I'm going to do is, instead of taking all of this data, I'm going to lop off some of it. So I'm going to randomly select 20% of it, and I'm going to pull it out. I'm just going to put it to the side. I'm going to fit the model on the other 80%. Okay. Then what I'm going to do is I'm going to take the model that I create. I'm going to run the 20% of the data that I just pulled to the side and put in the corner through that model. And I'll be able to evaluate how well the model works with data that it's never seen through what is now called a validation set. So what I'm going to do is I'm going to break this data into training data and validation data. Okay. Now there's a couple ways that you can do that. There's a couple ways that you can partition the data, and that's what I just explained. So you can partition the data the hard way. You can randomly sample data. You can use index location and cut off parts of the data if you want. So iLoc, you can do that, right? Let me show you an example. So I could do something like df2 equals df dot iLoc, which is short for index location. And I could simply just tell it, take the first 100 rows. So if I look at DF2, there's the first 100 rows of my data. I could do that. It's not the best solution because it's not randomly selected and you'd have to do a lot more work in order to get it there. So when in doubt, why not let Python do the work for you, right? Specifically SKlearn. So test train split, or the train test split function, is built into SKlearn, the library that we imported at the beginning. So instead of us taking the time to go through and actually split the data ourselves, partition the data ourselves, we can simply just create it. We can just create it on our own. So what we're going to do is we're going to create some variables first. So we're going to have x train, and we're going to have x val. Val is short for validation. So then we're going to have y train, and then we're going to have y val, which is again short for validation. So what we're going to do here is, instead of us partitioning it, we're going to use our train test split function that's built into SKlearn. And it's actually pretty darn easy to do. So all I have to do is I have to feed it my x predictors and my y target outcome, tell it how much I want to cut off the data, so how much data I want to use for validation, and then from there, tell it what the random state is. Okay, so let's do that. So the x value is pretty easy, right? Because we created it. So we're going to say that the predictors are simply x. And our target outcome, I hate that this pops up sometimes, so let's click off there. Okay, our target outcome is y, which we created on our own. Okay, so then we have to tell it what our test size is. And in this case, we want 20%. So let's talk about that for a second. Okay, so pretty much industry standard for partitioning data with training versus validation is 80% of all of your data goes to training, and the remaining 20% goes to validation. So now the thing about that is, it's a guideline, an industry standard, but it's possible that it could be all over the place. If you don't have that much data, maybe you do 90-10. And I don't think anyone would be that upset about it. But just when you're getting started out, the easiest thing for you to do is simply 80-20 split, right? So we're saying take 20% of the data randomly, pull it out, move it to the side. Okay, and that's going to become the X validation set, or the validation set of data. So it'll have an X validation and a Y validation data set. So now the next thing we're going to do is set our random sample, or excuse me, our random state. A random state could be anything, but we need to set it in the event that we want to go through and try some brute force strategies, meaning we want to run this again. We want to make sure that we're using the same validation set when we do brute force, or it could get kind of wonky with our results. So at this point, I can simply run this. And what did that do exactly? Well, let's take a look. So if I look at my X values that you had up here, there were 171 rows, 3 columns, right? So now if I look at X train, there's 136 rows, 3 columns, right? Because it took the 80%, and that's all we're going to look at. That validation set is now off to the side. So we don't have to worry about it anymore. And we can do the same thing with our X validation. There's the remaining data. Okay. So at this point, we're going to create our regression model. We're going to fit our model, and then we're just going to start using it. So let's do that. So we're going to declare a variable called LR for linear regression. And we're simply going to use, we're going to use that linear regression model. Okay. So then we need to fit the model. So we're going to go lr.fit. And we simply need to feed it its X and its Y values, right? So it's going to be X train and Y train. Okay. And there's really nothing to it. So there we go. We fit a model. It's all good. So now it's not enough to just fit the model. We actually have to evaluate the model to see just how good it really is. So to evaluate the model, we're going to want to look at a couple metrics that are really, really good for multiple linear regression, right? So we can look at root mean square error. We can look at the mean square error, the mean error. So let's take a look at some of those. In order to do that, first, what we're going to do is we are going to run our validation data through the model that we just created. So remember the 20% that we had before? We're going to take that 20% and we're going to pass it into our model. We're going to feed it to the model, and we're going to see what the model thinks the answer would actually be. So what I'm going to do is I'll do something called y estimates. like so. And we're going to do linear regression, that regression that we just created. We'll do dot predict. And you know what we're going to do? We're going to take our X validation data, right? So we're going to take our X val data and we're going to pass that in. When we do, then let's look at it. So we'll go estimates like so. And there we have it, right? So we took all of our 20%, so our 20% validation data, we passed it into the model that we just created, and it gave us its predictions. Now, what makes this so cool is that we know the answers, right? So if I were to simply look at my Y validation, right? So the outputs, I can look and see the difference between what it thinks it is and what it actually is. So the first prediction for our model was 9.59. The actual value was 8.40. The difference between those two, that is the error. Okay. The second one was 23.12. The second one really was 24.12. So the actual value was 24.12. The difference between 23.12 and 24.12, that one, that is the error. So if we took all of the errors, okay, so we manually calculated all the errors, and we then averaged them, we would get the mean average error, or we would get the mean error. Okay, that's a metric that we could actually look at. Now, if we were to square that, we would get the mean squared error. And if we would take the square root of the mean squared error, we would get the root mean squared error, which is one of the big metrics that we will use in order to evaluate. Now, here's the good news. The way that I explain that, that's how you do this mathematically. Do you actually need to do this mathematically? Heck no. You can let Python do the work for you. So what are we going to do? Let's calculate the mean error. Okay, so how do we do that? So we'll use that function that we just created, or that we pulled in from SKlearn earlier, the mean absolute error. So what do we do? All we need to do is pass in our validation data and our estimates. Oh, and I guess I should have displayed it. And there you go. You've got the mean absolute error, right? So the difference on average between the predicted values and the actual values is 1.48. Not too bad. Now, that being said, remember, this is a curated data set. So yeah, of course it's going to work. In the real world, data is way messier than that. So let's take a look at mean squared error. Okay. So mean squared error can confuse you a little bit because there is no root squared error. There's an optional argument inside the mean squared error function that gives you the option of looking at either one. So what I'll do is first I'll pass in, just like before, my validation data. Then I'll pass in my estimates. So all it's doing is comparing what you actually have versus what it thinks it is. Okay. And then what I can do in order to look at the difference between mean squared error and root mean squared error is I have this option in here called false, or it's called squared. And I have an option of false, or I have an option of true. So let's do both. Okay, so that's false. Nope. We can cheat a little bit. Let's just copy this so we don't have to retype everything. And then we'll change this from false to true. And I probably should have printed that as well. There we go. It tells us 2.98 is our root mean squared error. So now a note on this, you just want these numbers to be as small as possible. The smaller the numbers are, the less your error is going to be. And that's really what we're looking for. Now, if you wanted to go a little bit farther, if you were curious about that old metric of R square, we can do R square. I'm a big Excel guy, so when I declare a variable for R square, I always go with RSQ, which would be the function in Excel, but you could call it anything you want. You can call it R squared, whatever. I do RSQ. So for RSQ, for R squared, the function you're going to want to use is called score. So we'll do lr.score. And what we'll do is we'll pass in our X val and our Y val. And if we look at RSQ, it says, hey, 92%. That's pretty darn good. Okay, so let's talk about this brute force thing for a second because we're almost out of here. What's this brute force thing I was talking about earlier? So here's what we know. We know the performance based on the three predictors of advertising in Facebook, YouTube, and the newspaper. But what if we wanted to save ourselves some money, like an actual deployable thing? What if we wanted to make a decision here, some decision support? So say we want to explore what would happen if we don't advertise in the newspaper? Maybe we can save that money. Well, you know what we can do? We can simply remove this predictor of newspaper and then run everything again, which won't take that much time. Now, of course, depending on the size of the data, it would. But as I go through and look at this, it didn't actually make a big difference removing newspaper. So because it didn't make a huge difference removing newspaper, I mean literally almost no change at all, you know what we could do? We could just not advertise in the newspaper. Save ourselves some money, right? Let's try again, just to make it interesting. So what if we remove advertising in Facebook? So now all we're going to do is advertise in YouTube. Okay, so now that made a huge difference. Look at the root mean square error. This got significantly larger. Remember before it was like 2.9, maybe 3, somewhere in there. And when I took away newspaper and I took away the other option, all of a sudden this skyrocketed. So you know what this tells us? We do not want to stop advertising in Facebook. We want that Facebook back. Here, watch. Let me do it one more time. So let's bring Facebook back. So remember, the root mean squared error was 15. Now look what just happened. It went down to 2.98. So you know what that tells us? We definitely want to keep that. So now this process of me doing basically brute force trial and error, that's exactly what the brute force method of predictor selection is. There are better ways to do this, but if you're getting started, this is just a good way to get started and you'll be completely functional. So with that, my friends, I will let this tutorial stop. I hope that you found this enjoyable. It was super handy. I really like doing these videos. So, you know, like the young people say, like and subscribe, show me some love. I will come back. I take requests too. So I will come back and maybe we'll talk about something really cool next time, like KNN or something of that nature. So have a great day, friends. We'll talk to you soon.